Hello, everyone. So in our last lecture, we developed the quantum mechanical model of the atom. And what did we find out? Well, we found out that we can't treat an electron simply as a particle. We also have to think of the electron as a wave. And ultimately, this led to the result, as we went through and developed the model, that electrons occupy orbitals. Well, in this lecture, we're going to take a closer look at those atomic orbitals. And in particular, what we want to do is describe these orbitals, their shapes, their sizes, their orientations, using a system of values called quantum numbers. So let's back up a little bit. All right. Orbitals were the result of solving Schrodinger's equation. And Schrodinger was ultimately treating electrons as standing waves. And when we solved Schrodinger's equation, well, we didn't, but he sure did, it yielded many wave functions. And let's remember that a wave function is nothing more than an orbital. And so this means that if we get many wave functions as solutions, there are many orbitals. All right, within atoms. Atoms are comprised of many, many orbitals as a result of getting many wave functions as solutions. Now, each orbital, as it turns out, is described by a series of what are called quantum numbers, where the quantum numbers tell us something about the various properties of an orbital. Okay, well, what are the quantum numbers and what do they tell us about orbitals? Well, the first quantum number we're going to look at right here is called the principal quantum number. Now, the principal quantum number is given the symbol lowercase n, and it's almost always italicized. And in many ways, the principal quantum number correlates very closely to Bohr's shells. So notice that Bohr also used an n to designate each one of those shells. So, well, as it turns out, the value of n, the principal quantum number, is ultimately related to the size of an orbital. And the allowed values of n are n equals 1, 2, 3, 4, going on till technically, I guess you would eventually get to infinity. Now, how does this work? Well, as the value of n is increasing, the size of the orbital would therefore also be larger and larger and larger, and the electron in that orbital would be located at greater and greater distances from the nucleus on average. Let's write that down. So as n increases, okay, the orbital size increases. So as n increases, the orbital size increases. And this also means that the electron, any electron in that orbital, will be further from the nucleus on average. So, and the electron will be further from the nucleus on average. Oops, that's not how you spell average. On average. There we go. Okay. Well, just to give you an example here, so let's suppose we have an orbital with an n value of 5 versus another orbital with an n value of 3. Okay. Well, the difference in n values is an indication of difference in size. An orbital with a value of n equals 5 is going to be considerably larger than an orbital with a value of n equals 3. So pretty simple. So let's just write that here. Orbitals with n equals 5 are larger than orbitals with n equals 3. All right, well, that's simple enough. And again, I do want to show the parallel to the principal quantum number with Bohr's shells. And sometimes we say that orbitals with the same principal quantum number are in the same principal shell. So some of that language spills over into the quantum mechanical model. Now, the second principal quantum number we're going to take a look at is the quantum number called the angular momentum quantum number. Angular momentum quantum number. And the symbol we use for the angular momentum quantum number is the symbol L. Now the L is usually written in script form and it is italicized, is the usual way we see this. And as it turns out, the property of an orbital that L is related to is ultimately the shape of the orbital. Now, what are the allowed values of L? Well, it turns out that for each value of n, L is allowed to take on values starting at 0 and then progressing up in whole number values, achieving as its highest allowed value n minus 1. So the allowed values are whole numbers starting from 0 up to n minus 1 for each value of L. Sorry, for each value of n. So, for example, let's illustrate that here. Okay. If, for example, we have n equals 5 orbitals, n equals 5, well, the allowed values of L would therefore be, well, we'd start off at 0, then 1, then 2, then 3. We would stop at 4 because 4 is n minus 1. 5 minus 1 is equal to 4. And so the allowed values of L for n equals 5 are 0, 1, 2, 3, and 4. Or if instead n was equal to 3, the allowed values of L would be equal to, starting at 0, 1, and we would go up to 2 in this case because 2 is 3 minus 1, n minus 1. Okay. Now, it turns out that each value of L corresponds to a letter designation. And you might remember these letter designations from your time in Chem 10. So our L values can be 0, 1, 2, 3, 4. Well, it can keep going, 5, 6, dot, 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 dot. And for each of these, there is a corresponding letter designation. And you might recall these letter designations. When L is equal to 0, the letter that is used is S. When L is equal to 1, P. L equals 2, D. L equals 3, F. Now it turns out once we get to L equals 4, we pick up alphabetically. So since the letter before, all right, for L equals 3 is F, L equals 4 is given the letter G. And L equals 5 is given the letter H, and then I, and then J, K, and so on and so forth. Okay. The S, the P, the D, and the F letter designations actually come from early studies in spectroscopy, actually. And then once we figured out that there were actually more values of L, we said, you know what, let's pick up with this alphabetically, which is probably what we should have done in the first place, but we're going to stick with the historical approach. Now, it also turns out that orbitals that have the same n value and L value together are often said to be occupying the same subshell, which is also something you may have heard of from your Chem 10 days. So once again, if they have the same n and L values, they are said to occupy the same subshell. So for example, again, let's suppose in this example we have orbitals with n equals, let's take n equals 3 and L equals, let's make it 1. Well, orbitals with n equals 3 and L equals 1, let's remember that L equals 1 corresponds to a P designation. Well, we would say that these orbitals are in a 3p subshell. Let's write that over here. Or for contrast, if we have, say, orbitals, that's not how you spell orbitals, let's try that again. Orbitals with, let's switch it up a little bit, with n equals 5 and L equals 3. Well, if we have orbitals and n equals 5 and L equals 3, all of these orbitals are said to be in a, well, 3 for L is an F designation. We would say these orbitals are together in a 5F subshell. So that's how this works here. So that's the angular momentum quantum number. So now we've seen the principal quantum number, n, which is about size, angular momentum quantum number, which is about shape, all right, which we can also designate with letters, and that those with the same shape, those with the same value of L, are all together in the same subshell. Well, that's going to take us to the third important quantum number called the magnetic quantum number. As it turns out, the magnetic quantum number has the symbol lowercase m italicized with a lowercase l also italicized, again in script form. And we say that as m sub l. And as it turns out, m sub l ultimately tells us something about the orientation of an orbital relative to all the other orbitals found in that atom. So this is about orientation. Now, what about the allowed values for m sub l? Well, it turns out m sub l takes on values that start with negative L, and they proceed to increase in whole number increments to 0, and then continue on to increase in whole number increments until the maximum allowed value, which is positive L. And so from negative L through 0 up to positive L for each value of L. So let's write that over here. For each value of L. So m sub L depends on, well, it depends on L. So again, let's take a look at an example here. So let's suppose we have L equal to 1. L equals to 1. Well, if L is equal to 1, the allowed values for m sub L would be negative 1, then 0, then positive 1. Or instead, if we have L, in this case, let's try another value, equal to 3. Well, if L is equal to 3, m sub L is going to be negative 3, that's negative L, then negative 2, then negative 1, going up one whole unit value at a time to 0. But then we're going to continue up to positive 1, positive 2, and we're going to end off with positive 3, that's positive L. So a large number of m sub L values. Okay. Now, here's something else important about the magnetic quantum number, and that is that the number of m sub L values obtained for a particular subshell corresponds to the number of orbitals in that subshell. Okay, so what are we talking about over here? Well, in n equals 1. Sorry. All right, for L equals 1. L equals 1 is sometimes just referred to loosely as a p subshell. P subshell. Well, in that p subshell, we know the values of m sub L, we already worked them out previously, are negative 1, 0, and positive 1. So we got 3 values of m sub L, and this means that there are 3 orbitals in this subshell. And for the L equals 3 subshell, L equals 3 corresponds to F, so this is an F subshell. Well, we got m sub L values of negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. If we count them, that's 1, 2, 3, 4, 5, 6, 7 values. And as it turns out, this means that there are 7 orbitals in an F subshell. So the number of m sub L values happens to correspond to the number of orbitals in that subshell. Okay, let's take this information and combine it together in a table so that we can get a better sense of how all these numbers work together to allow us to organize our orbitals within just the first few levels in an atom. Okay. And I decided to just look at the first 4 levels of orbitals. So in the first case, let's take a look at when n is equal to 1. Now, when n is equal to 1, L, well, the allowed values for L are 0 up to n minus 1. Well, n minus 1 is 0, so that means the only allowed value of L is 0. Now, when L is equal to 0, well, what kind of subshell are we talking about? Well, it's a 1s subshell. So what did I do here? I used the 0 for L to get the S letter designation, and the 1 comes from the value of n, so it's the 1s subshell. Now, when L is equal to 0, the only possible value for m sub L is equal to 0. Because negative L to 0 to positive L, there's no such thing as a negative 0 and a positive 0, it's just 0. Now, we also know that the number of values of m sub L tell us the number of orbitals. And so since we only got one value of m sub L, there's only one orbital, all right, in the 1s subshell. And we call this one orbital a 1s orbital. So there's one 1s orbital in the 1s subshell in n equals 1. The n equals 1 principal shell, the principal shell. Okay. Now, when n is equal to 2, L is equal to 0 and 1. 0 and 1. That means we get 2 subshells in n equals 2. And what are they? Well, they are the 2s subshell and the 2p subshell. So again, notice that the 2 is coming from the n value, and that the letter designation corresponds to the L value. And that's how we get the subshell. Okay. Now, when L is equal to 0, we've already seen that the only m sub L value allowed is 0. But when L is equal to 1, m sub L can take on values of negative 1 to 0 to positive 1. So what does this mean? This means that when m sub L is 0 by itself, we have once again just one orbital in the 2s subshell. And we call that orbital a 2s orbital. So we have one 2s orbital. Why 1? Because we only have this one value of m sub L. But for the 2p subshell, we've got 3 values of m sub L. And so this means we have 3 orbitals in the 2p subshell, or 3 2p orbitals. Okay. Now, when n is equal to 3, well, the values of L that are allowed for n equals 3 are 0, 1, and 2. Now, when L is equal to 0 and n is equal to 3, we get the 3s subshell. When we have n equals 3 and L equals 1, that's the 3p subshell. When n is equal to 3 and L is equal to 2, that's now called the 3d subshell. Now, when L is equal to 0, the only allowed value of m sub L is 0. When L is equal to 1, we get m sub L values negative 1, 0, positive 1. But when L is equal to 2, our values are negative 2, negative 1, 0, positive 1, and positive 2. We got 1 ml value for the 3s subshell, which means once again there's only one 3s orbital in the 3s subshell. But we got 1, 2, 3 values when L is equal to 1, all right, for the 3p subshell, and 3 values mean that there are 3 3p orbitals in the 3p subshell. And, well, when L is equal to 2, we got 1, 2, 3, 4, 5 values that tell us there are 5 3d orbitals in the 3d subshell. And this is kind of crazy looking. It looks like, I don't know what it looks like, but that should be a positive 2. There we go. That's a little bit better. Okay. Okay, let's do one more level. And obviously you can keep going on your own if you want. You can do 5 levels, 10 levels if you want. We're going to stop at n equals 4. So in n equals 4, the allowed L values are 0, 1, 2, and 3. So 4 and 0, that's the 4s subshell. 4 and 1, 4p subshell. 4 and 2, 4d subshell. 4 and 3 gives us a 4f subshell. When L is equal to 0, m sub L is equal to 0. When L is equal to 1, we get values for m sub L, -1, 0, +1. When L is equal to 2, our m sub L values are -2, -1, 0, +1, and +2. And now, when L is equal to 3, our values are -3, -2, -1, 0, +1, +2, and +3. So what does this mean for orbitals? It means that we're going to have one 4s orbital in the 4s subshell. We're going to have, once again, 3 4p orbitals in the 4p subshell. There are 5 4d orbitals in the 4d subshell. And for the 4f subshell, we got 1, 2, 3, 4, 5, 6, 7. So 7 values of m sub L, 7 4f orbitals in the 4f subshell. And just for fun, why don't you, on your own, try working out the next level, which would be n equals 5, and see, what kinds of subshells do you get, how many orbitals do you get in each of those subshells, just to see if you are, well, getting the overall idea here. So let's talk about some of the similarities and differences between the various orbitals. So for example, if we wanted to compare, say, this orbital, this 1s orbital, with this 2s orbital, well, what could we say about these two orbitals? How are they similar and how are they different from one another? Well, for starters, they have different sizes. Why do they have different sizes? Well, all right, the first orbital is a 1s orbital. N is equal to 1. All right, but the 2s orbital is n equals 2. So the 2s orbital must clearly be a larger orbital than the 1s orbital. But what do they have in common? Well, their overall shape is going to be similar. Now, we haven't talked about the shapes yet, but we know that the L value is the same for a 1s orbital and a 2s orbital. All right, an S designation means L is equal to 0. And if they have the same L value, they're going to have the same basic shape. Now, let's suppose, in contrast, we wanted to compare the 2s orbital with these 3 2p orbitals. Well, what's similar and what's different about these orbitals? Well, what's similar about these orbitals is that they have the same relative size. Why? Because they have the same n value, 2s, 2p, n is equal to 2 for all 4 of these orbitals. All 4 orbitals are of n equal 2. They're the same size. But what's different? Well, one of them is a 2s orbital. All right, the other 3 are 2p orbitals. They're 2p orbitals. And, well, an s orbital is L equals 0. P orbitals are L equals 1. And, well, we know if they have different L values, they have to have different shapes. So the p orbitals are going to be differently shaped than the s orbital. All right, but since they're both n equals 2, they have the same, all right, size, the same size. Now, how about we then want to take a look at the similarities and differences between all 3 of the 2p orbitals. So just the 2p orbitals, and there's 3 of them. Well, what do they have in common? Well, they're all n equals 2, 2p. So they're all the same size. Now, all 3 of those orbitals have the same L value. They all have an L value of 1. And if they have the same L value, they all have the same shape. But do all 3 orbitals, all right, have the same m sub L value? No, they don't. One of those orbitals is -1, one of those orbitals is 0, one of these orbitals is +1. And what does the m sub L value indicate? It indicates orientation. So these three 3p orbitals could be expected to have the same size, the same shape, but different orientations since they all have different m sub L values. Okay, we're going to see more about shapes, orbital shapes, and orbital orientations very shortly, very shortly. So before we get to that, let's take a look at number 14. So number 14 from our ICE examples in chapter 7 says, which of the following sets of quantum numbers are not allowed? Which are forbidden quantum numbers. Ooh. Okay, well, let's take a look at each set of quantum numbers in turn. And what we're given is a value of n, a value of L, and a value of m sub L. N, L, m sub L. N, L, m sub L. All right, four sets of quantum numbers that we want to decide whether they are valid or if they are just not allowed. Okay, so let's take a look at the first. I'm going to use a highlighter here. In the first set of quantum numbers, we're given a value of n equal to 5. Now, the first question is that an allowed value for n? And the answer is yes. The value of n can be anything from 1 up to infinity. So 1, 2, 3, 4, 5. 5 is absolutely a perfectly good quantum number. So I'm going to put a check. That's good. Now, when n is equal to 5, what are the allowed values for L? Well, L can take on values of 0, 1, 2, 3, and 4. And so when I go over and look for the L value, which is given to me here as L equal to 1, is L equal 1 okay? You betcha. It's one of the allowed values. So I'm going to put check. That's okay. Now that we know that L equals 1 is allowed for an n value of 5, our next question is, okay, well, if L is equal to 1, what are the allowed m sub L values when L is equal to 1? Well, when L is equal to 1, m sub L can take on values of -1, 0, and +1. And what do we notice? We notice that m sub L equals -1 is absolutely acceptable, and that's what we're given here. And so in the end, this is an acceptable set of quantum numbers. They are a valid set of quantum numbers. They don't disobey any of the rules that we've already established. Now, in the next example, we have n equals to 3. Is that allowed? Absolutely. N can be 1, 2, 3, 4, 5, 6, 7, but yes, 3 is perfectly good as a quantum number for n. Check. Now, once again, when n is equal to 3, L can take on values of 0, 1, and 2. And we see a problem. All right, L can only be 0, 1, and 2 when n is equal to 3. It cannot be a value of L equals 3. That's an impossibility. That's not allowed. This is not an okay set of quantum numbers. So, nope, this is no good. It's a bad set of numbers. Now, in our third example, we're given a starting value, here we go, of n equals 4. And that's perfectly allowable. Any whole number starting from 1. Now, when n is equal to 4, L can take on values of 0, 1, 2, and 3. And so 0 is an acceptable value. So let's put a check here and a check here. Now, when L is equal to 0, what are the allowed values for m sub L? Well, when L is equal to 0, m sub L can only be equal to 0. And, well, that means this m sub L value is problematic. This is not a good set of quantum numbers. M sub L cannot be equal to 1 if we have a value of L of 0. And in our last set of numbers, we have a principal quantum number of 7, which once again is perfectly acceptable. Let's give it a check. And when n is equal to 7, L can take on values of 0, 1, 2, 3, 4, 5, and 6, up to n minus 1. And do we see a 4? Yes, there it is. That means that L equals 4 is perfectly allowed. And when L is equal to 4, what are the allowed values of M sub L? Well, they are -4, -3, -2, -1, 0, +1, +2, +3. I'm going to barely fit it in, +4. And when we take a look, well, there it is, the -3 that we were looking for M sub L, which makes this set of quantum numbers allowed. So the first and last set of quantum numbers are good, but the two middle sets are not allowed. Okay, so we've talked a little bit about how the angular momentum quantum number, which is L, ultimately relates to the shape of an orbital. Well, now we want to get into that in a lot more detail. So we're going to be taking a look at orbital shapes. So in our last lecture, we found out that the best way to represent an orbital is as an electron density map. That's the picture with all the little dots that shows ultimately the probability of finding an electron in a particular location within the orbital. Okay. Now, we can add a boundary surface to an orbital. And we also found out last time that that boundary surface indicates when 90% of the total electron probability is within that boundary surface. And when we add that boundary surface, it appears as if the orbital has a particular three-dimensional geometric shape. And that's what we're going to be focusing on. All right, these apparent three-dimensional geometric shapes that orbitals take on. Now, like I said earlier, the overall shape of an orbital is determined by its angular momentum quantum number, L. So there's a correlation between the value of L, 0, 1, 2, 3, 4, S, P, D, F, G, etc. All right, well, there's a correlation between that value, that letter designation, and the shape of an orbital. So let's just underline that. That's kind of important. So the overall shape of an orbital is determined primarily by L, its angular momentum quantum number. Well, the lowest allowed value for L is 0. And so the place we're going to start is orbitals with an L value of 0. And when L is equal to 0, all right, these orbitals are known as s orbitals. They're s orbitals. And, well, what is the shape of an s orbital? Well, their shape is spherical. They have a spherical shape, as we can see in this figure over here. So let's remember these are three-dimensional shapes, but it's really hard to draw a three-dimensional shape on a flat two-dimensional piece of paper or on a screen. And so we have our hypothetical axes, the x-axis, the y-axis, x-axis, the y-axis, the z-axis. They're arbitrary. You can label any of them x, y, or z, all right, to give a sense that this is a three-dimensional volume of space, which is spherical, and the nucleus would be right where the three axes cross, right in the middle. So the nucleus in the middle. Okay. Now, the orbitals with L equals 0. So this is an orbital with L equals 0. Now we know that the only allowed M sub L value for this orbital is also equal to 0. So let's write that a little bit better here. So we know that when L is equal to 0, the only allowed M sub L value, all right, is 0. So what does this tell us? Well, we only got one value for M sub L. And that one value tells us that there is only one s orbital, spherical s orbital, in every s subshell. So let's write that here. So there's only one s orbital in every s subshell. So every s subshell can only have one s orbital. Why? Because we only get one value of M sub L. And if we go back up here to our table It doesn't matter if we're talking about a 1s subshell, a 2s subshell, a 3s subshell, a 4s subshell. How many s orbitals? Just one s orbital in each of those subshells. Okay, well, let's move on to other shapes. Well, the next type of orbitals we're going to look at are orbitals with L equal 1, and these are known as p orbitals. And well, we can see that, all right, the shape of a p orbital is definitely more complicated. All right, they're often described as having a double-lobed shape. Oops, that should be an L, double-lobed shape. Okay. Now, each of these orbitals is L equal to 1. So this is L equal 1, this is L equals 1, this is L equals 1. They're all p orbitals here. But let's remember that when L is equal to 1, m sub L can take on values of -1, 0, and +1, where each of these values indicates the number of p orbitals in a p subshell. And this is why we have 1, 2, 3 orbitals represented here. So this indicates that there are always 3 p orbitals in every p subshell. But these p orbitals aren't 100% identical to each other. And as you can see from this figure over here, well, what's different about each of these p orbitals? Their orientation in three-dimensional space is different. So the first p orbital has its two lobes lying on the z-axis. The second p orbital has its two lobes lying along the x-axis, and the third p orbital has its double lobes lying directly along the y-axis. In other words, these three orbitals each have a different orientation. So we always have 3 p orbitals in every p subshell. All right, we're going to add here, each with a different orientation. Okay. Now, sometimes that orientation is given in the form of the letter designation and a subscript, where the subscript tells us where the lobes are. So this is called the pz orbital. This is called the px orbital. This is called the py orbital. Now, p goes together with an L value of 1. All right. The directionality, x, y, and z, well, that's indicated by the m sub L value. And so we might say that this orbital here has an m sub L value of -1, while this orbital here has an m sub L value of 0, and this orbital has an m sub L value of +1. Now, -1, 0, and +1 are arbitrary. So I could have just as easily said that the first orbital had an m sub L value of 0 and the second orbital has an m sub L value of -1. It's arbitrary. Just as x, y, and z are arbitrary. We decide what's x, what's y, what's z. So all the m sub L value is doing is telling us that these three orbitals have different orientations, just as the x, y, and z indicate different orientations. Okay, well, that's orbitals with L equal to 1, double-lobed orbitals, and always a pack of 3, always a pack of 3 in every p subshell. Well, what about orbitals with L equals 2? Well, they're known as d orbitals. And well, we can see from the figures below, all right, that these orbitals tend to be what we call four-lobed orbitals. Sometimes they're described as having the shape of a four-leaved clover. So these are four-lobed in shape. All right, mostly. Turns out 4 out of the 5 are four-lobed, but the fifth one has quite a bit of a different shape. Okay, well, once again, all of these orbitals are L equals 2 orbitals. This is L equals 2, L equals 2, L equals 2, L equals 2. Even this rather strange looking one here is L equals 2. And we can see for the most part, all of these orbitals have this four-lobe shape. Four lobes, four lobes, four lobes, four lobes, except for the very last one, which kind of looks like a p orbital with two lobes and then a donut going around it. Even though it looks different, it is still an L equals 2 d orbital. And we get that from the mathematical form of the wave function. So the mathematics works out to being essentially the same as the other four orbitals. Now, we know that when L is equal to 2, M sub L takes on values of -2, -1. Oops, let's write this underneath so I can have a little space. Here we go. So when L is equal to 2, M sub L takes on values -2, -1, 0, +1, and +2. That is 5 M sub L values, which explains why we've depicted 1, 2, 3, 4, 5 d orbitals. And as such, we always have 5 d orbitals in every d subshell. And you know what? I'm going to just erase this. I'm going to write it down on the bottom. Now, are all 5 orbitals identical? Well, even the ones that are four lobes show differences. And what are their differences? Orientation. So once again, we're going to have 5 d orbitals at every d subshell, each with a different orientation. Each with a different orientation. So when we think about those 5 lobes, what we can focus on is which lobes are between which axes. So for example, right here, the 4 lobes are lying between the z-axis and the x-axis. And this is why this orbital is sometimes called the dxz orbital. Whereas this orbital here has the 4 lobes lying right in between the x-axis and the y-axis, which is why it's called the dxy orbital. Over here, the orbital lobes lie between the y-axis and the z-axis, making this the dyz. So note that little subscript, the YZ, the XZ, the XY, is telling us something about the three-dimensional spatial arrangement of the lobes. Well, the fourth of those four-lobed orbitals, all right, is in the same plane as the one preceding it. Here's the x-axis and here's the y-axis. But we should note a particular difference between this and the one right before it. Over here, the lobes are in between the axes, but here they're right on top of the axes. So between versus right on top, and therefore it gets a different designation. All right, spatially, it's the dx squared minus y squared. And the one that doesn't look like it's belonging to this pack of orbitals, but actually is traditionally known as the dz squared. So watch out for this little guy. It looks a lot different from the other 4, but it is still a d orbital. Now, like I said before, all of these orbitals are L equal to 2 orbitals. L equals 2, L equals 2, L equals 2, L equals 2, L equals 2. But just as they are given a different subscript, dxy, dyz, etc., all right, what differentiates them with the quantum numbers is they get a different m sub L value. So over here, m sub L might be equal to -2. M sub L here, -1. M sub L, 0. M sub L, +1. M sub L, +2. And once again, these are arbitrary. So I could have just as easily made the dz squared m sub L value 0 instead of +2. It's meant to indicate differences in each of these d orbitals where the difference is orientation. Okay. Now, let's get to, all right, just one more set of orbitals, because what you're seeing, hopefully, is that these orbitals are getting more and more complex in their shapes. And I had to dig hard to find a set of F orbitals to show you. So orbitals with L equals 3 are called F orbitals. And as it turns out, since L is equal to 3, well, M sub L is going to have values ranging from -3 up to +3, -3, -2, -1, 0, +1, +2, +3. So we're always going to have 5 F orbitals in every F subshell. And well, how do you describe these shapes? Well, I'm just going to call them complex multi-lobe shapes. And aren't they beautiful? Quite fantastical. So let's just say they are complex multi-lobed shapes is what we end up having for here. But we're seeing a pattern here that the number of M sub L values indicates how many occur in an F subshell. And so once again, we always have 7 F orbitals in every F subshell. And once again, what are we seeing? Different orientations of these orbitals. And yes, all of them don't look exactly the same, but the mathematics still, all right, places them all as F orbitals. So each with different, what was I writing here? Orientations was the word I'm missing. Okay. So once again, each of these orbitals is L equals 3. L equals 3, L equals 3, L equals 3, L equals 3. Let's keep writing lots of L equals 3s. But to designate the differences in their orientations, we use a different M sub L value. So M sub L, -3, M sub L, -2, -1. And again, arbitrary, M sub L, 0, M sub L, 1, M sub L, 2, M sub L, 3 to indicate the differences in their three-dimensional geometries in space. Okay. Now, these are the orbitals I'm showing to you because this is as far as I can get without getting really fantastical shapes. But let's just think about it. Let's suppose we have a set of orbitals with L equal to 4. What would we call those orbitals? Well, after F is G. There would be G orbitals. Now, how many G orbitals would you expect to find in a G subshell? Well, it depends on how many M sub L values you get. If L is equal to 4, M sub L would go from -4 to +4. Count the values. And what you'd find out is we would have 9 G orbitals in a G subshell. And we could keep going and going and going, but we're not. We're focusing on the orbitals that are more important in ground state atoms, which is what we're really interested in. Okay, so now we've taken a look at the various shapes and orientations of orbitals and subshells. Well, we're going to get another important aspect of orbitals and particularly electrons, and that is something called electron spin. Electron spin. So, as it turns out, studies of electrons in magnetic fields reveal that electrons all have a property known as spin. Okay. Now, what is spin? Well, it's a basic property of all electrons, rather like all electrons have a negative charge. Now, when we study spin, we find out that the orientation of electron spin is quantized with only 2 possible states. And we like to indicate those states as an upspin and a downspin. Upspin and downspin. Okay, so we can envision electrons as either particles or waves. To get a sense of what spin is all about, let's envision an electron as a spinning particle. Think of, for example, a spinning top. So let's draw an electron as a particle. That's a rather large electron, but All right, here's our electron. And let's suppose it's spinning like a top around its axis, or like the world spins around its axis. Now, an electron spinning about its axis can only spin in one of two directions. It either spins clockwise or it spins anti-clockwise. Okay. Now, depending on the direction of its spin, we assign one of these directionalities as an upspin and the other as the downspin. So, and it's arbitrary which is which. So we might say that this one is the upspin and this one is the downspin, but it's entirely arbitrary. Okay. And to indicate electron spin using symbolic notations, we typically use arrows. We use an arrow pointing up to indicate an electron with an upspin and an arrow pointing down to indicate an electron spinning with its downspin. Okay. Now, what does this have to do with magnetic fields? Well, an electron, we know, has a negative charge. So this electron has a negative charge, this electron has a negative charge. Now, as it turns out, and this is something you may have studied in physics, but no big deal if you haven't, a charged particle in motion produces a magnetic field. Now, what do we have here? Spinning charged particles, particles in motion, and that means these two representations of spinning electrons are producing magnetic fields. Now, an electric field is indicated using plus or negative signs, but a magnetic field is typically indicated using north and south notations. Turns out that if you change the direction of an electron spin, you change the direction of the field that is generated. So, for example, if an electron with an upspin generates a magnetic field with north here and south here, poles in the magnetic field, the electron spinning in the opposite direction is going to have the poles reversed, south here and north here. And as it turns out, this is how we discovered spin. By placing electrons in magnetic fields, we noticed they behave differently. And they were behaving differently based on whether they had an upspin or a downspin. Now, because there are only two possible spins, making spin quantized, we need a fourth quantum number, and that fourth quantum number right here is called the electron spin quantum number. And the electron spin quantum number is given the symbol m, again italicized, with the subscript s, m sub s. Now, since there are only two possible spins, there are only two possible allowed values for m sub s, and that is positive a half or negative a half, where positive a half is typically assigned to an electron with an upspin, and negative a half is assigned to an electron with a downspin. Okay, well, we're almost done with this lecture. I know it's long. A lot of these lectures have been long recently, but we're going to push through it. And the last thing I want to talk about, all right, for this particular lecture is something called the Pauli exclusion principle, which is now going to tie, all right, these spinning electrons together with the orbitals that we have been describing in the lecture. So the Pauli exclusion principle was formulated by, well, a scientist named Pauli, Wolfgang Pauli, in 1925. Ultimately states, and this is rather important, I'm going to underline this. Let's get my yellow highlighter. He states, in a given atom, no two electrons can have the same four quantum numbers, where the four quantum numbers are now n, l, m sub l, and m sub s. Okay, they can't have all four values identical. In other words, each electron in an atom must have a unique set of four quantum numbers. This is rather like, say, your student ID number. Your student ID number is a collection of digits, and you and another student cannot have the same digits in your ID number in the exact same order. Otherwise, you'd have the same ID number, and that's no good. Each of you needs a unique ID number with a unique set of digits. All that's needed is for one digit to be different between you and another student, and you have a unique ID number. Well, it's the same idea here. All right, no two electrons can have the same exact four quantum numbers. Now, we just found out that electrons can only have two spin values, plus a half or minus a half. They have an up spin or a down spin. So what does this mean? Well, we know that if electrons in the same orbital, well, if we have electrons in the same orbital, they're going to have the same values of n, l, and m sub l. Well, if they're in the same orbital and these three values are the same, all right, in order to make sure they don't have the fourth quantum number the same, they must have different m sub s values. Now, we know that there are only two possible values of m sub s, plus a half or minus a half, and so the net result of the Pauli exclusion principle here, and I'm going to star it because it's so important, is this, that an orbital can only hold two electrons. That's the maximum in any orbital, regardless of how big or small it is, regardless of its shape or its orientation. Every orbital can hold a maximum of two electrons, and they must have opposite spins. So let's write that here. An orbital can only hold two electrons, and they must have opposite spins. That is the really important result here. Two electrons per orbital with opposite spins. Okay. Now, typically, the representation we use for an orbital with just two electrons in it with opposite spins is to use a square to depict the orbital. Obviously, there are no square orbitals. They're spherical, double-lobed, four-lobed, but we're not going to draw all of those fantastical shapes. So we use a square to indicate an orbital, and to show that there are two electrons in the orbital with opposite spins, we use the arrows up and down. And that is a symbolic notation that we often use to show the two electrons per orbital with their opposite spins. Now, I want to go back a little bit to that table we created. So let's go back a couple of pages, back, beep, 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 beep. Yes, I'm the truck. Okay. And what I want to go back to here is taking a look at this table where we looked at the number of orbitals. So let's notice that in n equals 1, we ended up with just one orbital, one 1s orbital. Well, in this 1s orbital, how many electrons can we put in this orbital? Well, we can get 2 electrons maximum in this orbital. Now, in n equals 2, we got one 2s orbital and three 2p orbitals. 1 plus 3, that's 4 orbitals. So if we have 4 orbitals, in n equals 2, and each of those orbitals can hold up to 2 electrons, that means the maximum number of electrons in n equals 2 must be 8 electrons. In n equals 3, we have one 3s orbital, three 3p orbitals, 5 3d orbitals, 1 plus 3 plus 5. Well, that's 9 orbitals. 9 orbitals times 2, that's 18 electrons maximum. In n equals 4, we have 1 4s, 3 4p, 5 4d, and 7 4f orbitals. That's 25 orbitals. 25 with 2 electrons apiece, we can get up to, 25 times 2 is 50 electrons max. And it turns out that these numbers correspond precisely to what Niels Bohr predicted in the Bohr model. Now, he wasn't looking at principal levels. He was looking at shells. He was looking at energy levels. But I should note that this number here that we just wrote in corresponds to 2n squared, which we met back in the Bohr model, which is a lovely tie-in with that Bohr model that I wanted to point out. Okay, let's go back to the last page once again. Back to the last page. Look at all the pretty stuff. Okay, and let's do a couple of examples that focus on electrons in orbitals, namely how many fit into orbitals. And let's take a look at two examples, numbers 15 and 16. So number 15 says, how many electrons in an atom can have the following designation? And three different designations here are given, 5F, n equals 2, and 4dxz. Okay, well, let's start with the designation 5F. The designation 5F is a subshell. It is the 5F subshell. Okay, well, a 5F subshell is composed of a certain number of orbitals. How many orbitals are in the 5F subshell? Well, we just found out that every single F subshell will be composed of 7 orbitals. 7 orbitals. I'm going to draw those 7 orbitals as 7 boxes. 1, 2, 3, 4, 5, 6, one more, 7. Not a thing of beauty. You can do better. So here are my 7 orbitals in my 5F subshell. So let's note that a 5F subshell is 7 orbitals. Now, how many electrons can we put in each of these orbitals? Well, we can put 2 electrons in each of these orbitals, and they must have opposite spins. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So how many electrons can have this designation here of 5F? Well, this 5F designation tells us that we can have 14 electrons with that designation. Okay. Now, in the next example, we have n equals 2. Now, n equals 2 is not the designation of a subshell. All right, n equals 2 is the designation of a principal shell, or it's just the principal quantum number. So I'm just going to say that this is a principal shell designation. Principal shell. Well, how many subshells and how many orbitals are in the n equals 2 principal shell? Well, when n is equal to 2, we know that L is equal to 0 and 1. That means in the n equals 2 principal shell, we have a 2s subshell and a 2p subshell. So these are our subshells. Now, how many orbitals are in the 2s subshell? Well, 1 orbital is in the 2s subshell, which I can draw like this. How many orbitals are in the 2p subshell? Well, 3. There are always 3 orbitals in the p subshells. So now I have the 2s subshell and the 2p subshell shown here with the correct number of orbitals. So how many electrons? Well, 1, 2, 3, 4, 5, 6, 7, 8. And so the answer here is that 8 electrons can have the designation n equals 2. N equals 2. Now, in the third example, we have 4dxz. 4dxz is very specific. And what makes it very specific is that subscript xz at the bottom. 4d by itself refers to the 4d subshell, but 4dxz specifically points out one of the orbitals in the 4d subshell, and that's what we have here. So this is one orbital in, all right, the 4d subshell. Well, let's take a look at the 4d subshell. The 4d subshell is composed of how many orbitals? Well, if it's a d subshell, all d subshells are composed of 5 orbitals. 1, 2, 3, 4, 5. All of these are 4d orbitals, okay? But each d orbital has a different orientation. So one of these d orbitals is d, y, xy. One of these orbitals is d, xz. One of these orbitals is d, yz. One of them is dz squared, and one of them is dx squared minus y squared. And in this example here, all right, we are specifically focusing on just one of these orbitals, all right, for dz. And, well, how many electrons can answer to that designation? How many electrons? Well, it's just 2. And that's because any individual orbital can only accommodate 2 electrons maximum. Okay. Now, in the second example, we're going to do the same thing, but with quantum numbers instead. So number 16 says, how many electrons in an atom could be described by the following quantum numbers? So we're given a set of quantum numbers, here n and l, here n, l, and m sub l, and in the third set we have n, l, m sub l, and m sub s. And so we need to be able to interpret, all right, what these quantum numbers are telling us. So I'm going to just scroll up to squeeze in this last problem. So let's start over here with the example n equals 4 and l equals 2. N equals 4, l equals 2. Now, when n is equal to 4, which is a perfectly valid quantum number, l can take on values 0, 1, 2, and 3. In other words, n equals 4 has a 4s subshell, a 4p subshell, a 4d subshell, and a 4f subshell. Now, we're not interested in all of these subshells. In this problem, we're interested when L is equal to 2 and N is equal to 4. These numbers here. So we're just interested in the 4d subshell. Now, if we're talking about the 4d subshell over here, that's what n equals 4, l equals 2 is telling us. How many orbitals are in the 4d subshell? Well, every d subshell has 5 orbitals. So this 4d subshell is composed of 1, 2, 3, 4, 5 orbitals. Okay? And every one of these 5 orbitals has n equals 4 and l equals 2. So that's their n value and their l value. And, well, how many electrons can be described in this manner? Well, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all right, have the quantum numbers n equals 4 and l equals 2, 10 electrons. Okay, now in the next example, we have n equals 5, l equals 1, and m sub l equals positive 1. So let's start with n equals 5. In n equals 5, we have L values of 0, 1, 2, 3, 4. In other words, it is possible for us to have a 5s subshell, a 5p subshell, a 5d subshell, a 5f subshell, and even a 5g subshell. But the only L value that matters here is L equal to 1. And so what are we looking at? Well, for starters, we're looking at a 5p subshell. Now, how many orbitals are in a 5p subshell? Well, it doesn't matter if it's 2p, 3p, 4p, 5p, or 100p. Every single p subshell is composed of 3 orbitals. So let's draw 3 orbitals. 1, 2, 3. Now, every one of these orbitals has the same n value. 5, 5, 5. That's their n value. And they all have the same L value, 1, 1, 1. But we have information other than N and L. All right, right here, whoops. All right, we have the M sub L value. M sub L is included. Now, do these three orbitals have the same M sub L value? No. We know that when L is equal to 1, M sub L is equal to -1, 0, and +1. So now, all right, what we see is we're not looking at the whole subshell. We are just looking at this one orbital. Only this one orbital has n equals 5, L equals 1, and M sub L equals +1. So in this case, only 2 electrons can be described by this set of quantum numbers. Okay, well, in our third example, we're going to start out with n equals 3. Now we know that when n is equal to 3, L can take on values of 0, 1, and 2, meaning that we can have an S subshell, whoops, a 3s subshell, a 3p subshell, and a 3d subshell. Now, the L value specified here is 0, and that means we're interested in focusing on the 3s subshell. Okay, now how many orbitals are in a 3s subshell? Well, it doesn't matter if it's a 1s, a 5s, a 15s, or a 3s subshell. All s subshells are just one orbital by themselves. So I'm just going to draw one lonely orbital. I'm going to draw it a little bit bigger. You'll see why in a second. There we go. So this orbital has n equals 3 and L equal to 1. But we have some more information. All right, we have an M sub L value and an M sub S value. Well, I know that M sub L has to be equal, oops, that's supposed to be a 0 for L. There we go. Right at the end of the lecture is when I start making mistakes. So for the orbital, which is the 3s orbital and a 3s subshell, one orbital by itself, one lonely orbital, all right, n is equal to 3, L is equal to 0. Now, when L is equal to 0, the only allowed value for M sub L is equal to 0, and that takes care of this quantum number. Okay. Now, how many electrons can go in this orbital? Well, we know a maximum of 2 electrons can go in this orbital. But what's different about these 2 electrons? They have different spin quantum numbers. So we might designate this electron here a spin quantum number of +0.5, and this electron here, the downwards one, a spin of -0.5. And this here is their M sub S value. Okay. Well, in this case, M sub S is specified as -0.5. How many electrons have all 4 of these quantum numbers? Well, there can be only one, and it's this electron by itself. So the answer here is just one electron has these 4 quantum numbers. And this is actually what Wolfgang Pauli said. Every electron has to have a unique set of 4 quantum numbers. So 4 quantum numbers, as long as they are correct quantum numbers, is a description of one electron, just one electron in an atom. And a different electron will have a different 4 quantum numbers. Okay, so now we've taken a look at orbitals in atoms. Fun stuff. Next up, we're going to see how to place electrons in all of these orbitals in the right order. We're going to be looking at electron configurations and orbital diagrams. Fun stuff that you've seen before. So until then, take care, and I'll be talking to you all soon. Bye now.